let's continue. And so we saw both our pointers. We can create them. We can get the address of some data and get that and basically store it in a pointer. And then of course we can dereference. And if we have something more complex, such as structure, right? Like we have structure, right? We have some property, some attribute. Then of course we use the arrow syntax, right? We want to use the arrow syntax instead of the actual full syntax, right? Which just looks ugly, so we save 2 characters, right? 1, 2, 3, 4, and this is 1, 2, right? Shorter, right? We're all programmers are lazy programmers. Okay, now let's look at some more dynamic variables, right? So what's the idea? Basically, you probably heard of stack and heap, right? So where we store our data, right? So heap, well, codes in Latvian, right? A big heap of data, right? You think of it, right? It's a memory heap available for general allocation, right? And we assign, well, we create them doing execution, right? So on basically single variable or array of variables, right? So it assigns on heap, right? Not on stack. Right, so the base 2 places where you store data, basically, roughly speaking, very, very simplistic, right? So, again, this is C++. In C we use malloc or calloc, right? So, to dynamically assign memory or allocate memory. So, what's the issue, of course, with this new? You have to be very careful with this, right? Because if you allocate memory dynamically, what should you be doing? At some point, what you are expected to do later on, you stop, yeah, you have to remove it, delete it, basically. You need to also manage this memory, right? And usually this will not be a problem, but it can lead, if you don't manage this, and this is why C++ has this bad reputation, of course it can lead to memory leaks, meaning you are allocating some memory, blissfully unaware that your memory basically starts accumulating some, if your application keeps running, right, and your memory usage grows because you keep allocating memory, but you are not freeing it up or not deleting the unused memory. How do we solve this in modern language? When I say modern languages, well, there are a couple approaches, right? Most languages which we use these days, like Python, Java, Go, Kotlin, JavaScript, and so on, what do they include? They include something called garbage collection or garbage collector, right? Which counts these reference, look these pointers. Is anybody using this memory, right? As soon as the memory is not used, it's being removed, right? And we don't have to worry about it. It's very convenient, but you lose some speed. Again, sometimes this garbage collector has to run, has to count the references, maybe every half second, every second, right? It can lead to some performance issues. That's why C++ is generally, along with C, of course, is manual memory management. It leads to the fastest performance, right? Among other things, other reasons. Of course, there's language like Rust. You probably, again, we'll look at Rust next semester, right? In programming languages, right? Anyone has tried Rust already? Not yet. Good. That's okay. I mean, it's good. It's Rust is a good language, but it has a completely different approach. It's kind of in between, like you say. It has this infamous borrow checker. We'll talk about that next semester. But yeah, for now, so we'll look at C++. Right? We create summer memory, right? So, what's interesting is that this is a pointer actually, right? Looks like it's address, right? You allocate, you store the address, meaning you don't get directly, right? New integer here in this approach, right? So let's look at dynamic allocation. Dynamic alloc, right? Right, let's do this. Let's explore use of dynamic. We use new and delete keywords, right? So include iostream using right. Okay, let's do some standard. Sure. Okay. Let's keep doing this standard. This will already start with more complex structure, student, right? We don't have to. Yeah. It's copying from my previous, right? So okay. All right. But not necessarily. So int, right? Main. let's first let's allocate dynamically some integer, some single integer. Right. So this is a pointer, right? It's a pointer, new integer, right? We are saying here's some space for some memory, right? And this is relatively rarely used because usually, again, oftentimes, you know, for single pointers, yeah. Okay, so let's allocate. So we need to store. We have so we have memory address, but nothing specific stored in it, right? Whatever was there previously, right? So how do we do it, right? So this is assignment. So we say the value of the memory address is 5, right? The reference is okay, yeah. 5, and of course we can print it, right? Right, and we can also print, and then you can delete it. Yeah, summary. No more, right? So the thing is, right? Yeah, the pointer still exists. The memory, so it is not needed anymore, right? So we should not use P anymore at this point, right? All right. So let's see this. We should always delete memory element, right? Even though, yeah. So that's the thing. There was a question this on a Stack Overflow maybe like 10 years ago, right? Yeah, technically, nothing horrible would happen if you delete here, right? In this case, we skip this, right? Right. There was a discussion about this. So the simple example. Dynamic allocation, output dynamic on yes, value of memory address is 5, and actually we can print it. Let's output this memory address. Right, memory address. Alright, so memory address, there's some we put some value, now we should not use P anymore. Okay, so that's a simple example, right? So we can also, of course, say, okay, we want memory enough space for multiple, right? So this is we check this, right? This name, right? Delete, right? So memory leak. Previously allocated memory that cannot be reallocated, right? So basically, right? So we should be using delete, right? To deallocate memory delete operator, right? So sometimes, of course, you might need to delete the array, right? So let's look at this. Let's allocate now, right? Let's allocate memory for a single structure student, right? Yeah. So let's fill it out. So now we manually do it, right? Yeah, again, in production, use std string, right? And because it's from standard library, right? Yeah, this is include. So include for C strings we need. Yeah, C string. I think this is it. No. Where did this come from? String copy. Let's see the C++ reference. I think it's from old C++. C reference still exists. I think it still exists. Yeah, I shouldn't really be using this. But it's not okay, so let's see. String H, sorry, string H, not C string, but CH, okay, string H. String H, right. Okay, first string copy first. Now it should be available. Yeah, it is. Okay. Alright. And so now we can print it, of course. Now. But of course, what we could do is, right, so this will work, right? And of course, we can delete it. Now, we can now delete student, right? We bring memory, it's not needed anymore, right? So, compiles, no problem. Dynamic, yes, of course, we have some memory address, right? And we have student ID and so on. Okay, so this is all pretty simple. Again, so why would, again, for singles, again, the issue is where we store data, and we don't use this new keyword, right? We assign some memory, right? It's stored on stack. This is where we store it on a heap. On heap, not stack. Not stack, right? All right. Now let's create a multiple. So now, usually we would allocate. So why for single? So for single values, we do not necessarily, right? Not usually, right? Usually no need, right? No need. Stack has space is fine, right? For we usually use new and delete for arrays of data, meaning we want megabytes, or even gigabytes, right? I don't know, terabytes, well, possibly terabytes, I don't know, possibly terabytes on some huge servers, right? So that's when we say, okay, I want a lot of memory, give it to me, right? So let's do that. Okay, so 10 integers. Oh, yeah, so this is okay, fine. Right. So we're saying we're allocating memory for 10 integers, right? So this is a pointer array, right? Again, we just have the memory address of first element, right? We do not know what is in it, right? Also, without the length, without knowing that, also we do not know how many elements are in an array, right? Right? By default, right? Let's take a look. So, right, so let's assign some values. Let's assign some values to the first 7 elements. Right? You know, some values, right? Now let's print 15 elements, right? We don't actually have them, right? We do not actually have 15. We have 10, out of which 7 are initialized, right? But the thing is, C++, so we are accessing some memory that we do not own, right? So this is, again, this is very bad. This is very bad. I like doing bad things, right? So compile. Yes, you see, okay. So look at the results. So first 0, right? So 0, 10, this looks good, right? These first 7 look good, up to, right? And then we get magic, right? So some things have some, complete garbage, right? And some things have 0 values, but again, you cannot depend. So what happens? So this is the interesting moment here. Actually, it's the same, right? This actually, so this is what something people might not understand is this part here, actually, right? Turns out, actually, array E is same, yeah. So this is what's very interesting, right? So basically, we get, right? So CO. Right. So in syntactic sugar,
So, and what's even more worse actually is you can reverse it actually, right? But show you that, right? So let's compile. Right. So in this case, yeah, again, you can see the garbage continues, but the good stuff happens, right? So you can see again. So now you trust me that this actually is the case, right? So this is right. Yeah. 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 Right. So again, if something this happens, again, of course, usually access doesn't, by accessing, you can imagine this is not a big deal, right? But the real problem would be, of course, right? Yeah. Even worse would be a changing or memory that you do not. Right. So that's even worse, right? If you say, okay, I'm going to put 5,000 in the memory address here, right? And that is used by some other, just imagine what's happening, right? This leads to the biggest bounce, right? That leads, right? That would lead to catastrophic failure of the program. Even the whole system, right? Depends on memory management, right? So that's the thing why C++ is dangerous, right? So again, so you need to, so this means you need to manage your size. So you need to keep track of the memory you have allocated, right? Right. So in this case, right? In this case, then, so you should have used some const like size 10, R size, R size 10 to keep track of the size, right? That would be my advice, right? So again, bad code, right? Right. So we get memory, right? And of course, again, let's read this memory. So this is delete. So notice these brackets, right? You need to freeze the memory, right? It's not needed anymore, right? Okay, but again, we'll do more of this later on as well. Okay, let's see what's happening. There's some more material here today. Lecture, right? Operators on pointer variables, right? Assignment, right? Yes. So what we saw here, right? There is a pointer arithmetic. Yeah, this is pointer arithmetic, right? So this is pointer arithmetic. This pointer arithmetic. So what's the difference between regular arithmetic? Yeah. Print address. Yeah. So this part here. Yeah, this is using pointer arithmetic. So pointer arithmetic. So it is. So that's the thing. So size of integer in this case. In this particular case, right? Because integer, right? Because we are storing 10 integers, right? So this part here is pointer arithmetic, right? We're not adding just one. We're adding probably it's going to be 4 or 8, depending how big your integer is, right? Size of integer, right? Size of integer. Print size of integer on this system. Yeah, all right. So it's probably 4 or 8. I think 8. So 8 will be 64-bit integer, right? So again, it's not necessarily depends on your compiler, right? It depends, of course, on your OS, right? I think, let's see. It's actually 4, yeah. Okay. So you see here, okay, you can see the pointer arithmetic. Look at this, what's happened, right? So I assigned only 10, right? So it's 4 bytes, 4 bytes, 4 bytes, 4 bytes, 4 bytes, 4 bytes, right? Unfortunately, I start here, right? Keep going up. 4, 8, C, and no, this is F, right? 16. So it's a hexadecimal, right? 4, 4. Again 4, C again. So 2F, after 2F comes 3, 0, right? Yeah, we had 4. So 3, 0, 0, 0. Now, and again, the thing is, of course, here, what's interesting, of course, is there's 10, right? Still, they keep going up, but unfortunately, we don't own, remember again, we don't own any of these 3, 4, 5, sorry, 5. We don't own any others of these, right? These are just garbage, complete garbage. we shouldn't really access. These we are accessing. It's sort of their own. These are our own. 1, 2, 3. Unfortunately, none of these are initialized, right? We don't know what's inside. We have zero guarantees on guarantees what's inside. Okay. All right. So that's enough. A little short refresher on pointer arithmetic. Let me sort. Allocating and freeing memory. Now, so pointer arithmetic, dangerous, very dangerous stuff, right? Dynamic array, like we already saw this, I already showed you this, right? We can again, this is just a pointer magic. What's funny thing is actually is that we have all this part here. One lap before delete, I'll show you one trick. So technically, using so to access third element of array, we can use you can use this, or even what is even scarier, we can use this part here. No, we can use this. I believe it's. I think so this is. Let's try this. I think it works. I believe it still. At least on C. It used to work on C. I think it still works. Not anymore? Oh, I guess not. That's good. I guess it's good. So we can use but I guess luckily it's not I thought we could, but yeah, it used. I guess maybe they fixed this, right? I thought it's in C, but there was a way of doing it, because I guess I'm not gonna have to. Don't do this. So don't do this actually, right? Okay, don't even do it. All right, let's keep going. Yeah, so you can have, of course, this is a pointer to the pointers, right? Pointer to the pointers, right? Because you have a dynamic memory and you have memory allocated. So again, in practical terms, again on midterm, you don't have to do this. You can use vector or vectors. It's much easier, much safer. Again, prefer using these pre-built structures, so these dynamic memory allocations. Well, you need a lot of memory and you don't have any ready-to-use structures to hold it, right? So, again, a couple more concepts before we move on. What's shallow copy? Shallow copy, when they are basically just storing, we're looking at memory addresses, right? We just say, okay, here's memory address, right? Whatever you want to do it, whatever is allowed, you can do it. But deep copy, of course, is when we copy the actual data. And we see this in all languages, like in Python, when we copy something, or do we have reference? Again, most languages hide these pointers, right? We don't see the actual pointer addresses, usually, unless we try to look at, right? So, reminder that some things are copied directly, right? So, you have a class, or structure, right? And you copy, right? So, they are, well, two different objects, right? Yeah, so, all right, so, destructor, right? You need to, of course, so in a destructor, right? If your object is allocating some memory, right here, there's some memory, right? You need to, of course, clean it, right? You need to clean it, right? All right, there's copy constructor. Let's see here, right? Assignment, right? Right. After shallow copy, if deallocate. So the problem is, of course, if it is a pointer, right, and you are freeing, so this is where the really nasty bugs could appear, right? If you have a pointer, right, and it's actually pointing to the same address, and one of your objects is deallocating, freeing, deleting the memory, right? But second object, right, is also still pointing to the same memory. You're trying to get the data, but it is not. It should not be. There are no guarantees anymore. It should be. It's freed. It's maybe used by something else, right? And you try to do something. This can lead to hard to catch bugs, of course. All right. So So passing by values, right? You know, obviously declare initialized using value of another object. Obviously pass by value as parameter, right? And you want to return something, right? So, so one solution, of course, use a constant override the copy constructor. Bless you. Yeah. Include copy constructor, right? Compile binding, right? Right. So, last thing I want to look at today. Let's look at this at the virtual functions, right? Binding, of course, is program execution time, not compile time, right? So, not declared is reserved for functions. So let's look at the C++ references about this. C++ reference virtual function, right? Yeah. Yeah. So virtual, when I write something virtual, especially as a non-static member function, is virtual supports dynamic dispatch, right? Right. So, meaning we can override the functions, right? Yeah. So overriding behavior is preserved even if there's no compile time information about the actual type of the class, right? So, if we derive classes handled using a pointer, right? Pointer virtual function would invoke the behavior defined in the derived class. Let's look at an example. We have a base. We are deriving something, right? So look at this here, right? We type it virtual, right? Again, you don't have these problems if you are not inheriting, right? You don't do inheritance, you don't have this problem. But here you are inheriting, right? And you say, okay, virtual void function, right? And you say, okay, same signature, void f, right? Override is optional. Actually, it says okay, but basically, right? This is our own function. This is a new function, right? So, which one we call? So br, it's a base function, right? Prints base, right? br. Let's see why is dr base at dr address, right? Right? By reference, right? Derived function, right? Derived function equals d, right? We create two objects. We create two objects, right? Static creation, right? So virtual function called through pointer, right? We have a pointer, right? Base derived. So this looks okay, but non-virtual function call, right? So this is a little bit tricky, maybe too much. And again, non-virtual function call base, right? So that's what's maybe a little bit tricky, right? You call by pointer, it will be base and derived. And here you get actually non-virtual call, you get base in both cases, right? So that's when you see virtual, right? This probably deals with things can be overridden. Okay, again, one more thing of complexity. Again, will this be on a midterm? Nope. I will not ask you. So that's why I'm not gonna say kill you, but I'm not going to how should I say, torture you too much on this one, right? Again, so runtime binding, yeah, the not generate code of this function only at the time, right? So derived class, slicing problem, right? On the virtual destructor, but I want to get to the abstract class. Okay, so that is okay. That might be so because we want to create a. We will get this, to this part here. So abstract class is you don't have an implementation. You just have some definitions, right? Derived classes inherit existing members of base class. You can add their own members, right? And they define or override public functions. So abstract classes, right? So abstract classes is a class with one or more virtual functions, basically, right? So it can contain instance variables, constructors, right? It must provide the definitions of constructor functions that are not pure virtual, but, right? Pure virtual functions do not have any definitions, right? You say, okay, it's a virtual, right? And that's it. No definitions, right? Let's look at an example right here, right? We have 10 minutes. I don't know if we can do this, right? So create an abstract data, a list, basically, right? We'll create an abstract data type, which is a list, basically. This is maybe a little bit too much, right? Let's do this. Abstract, and let's see an example, right? Let's see an example. We don't have an example here. Let's do an abstract class. Maybe we'll do. Let's see. Do we have more What we're going to do next week? Let's take a look. Maybe we'll take a look at the. Let's look at the overload. Okay, we'll do overloading, templates, exception handling. Okay, that's good. All right. So let's look at this here. Dynamic allocations. Let's do abstract. Let's create an abstract list class, some basic methods using, all right? Yeah. We don't know. For now, for integers, we assume we do not know about templates yet. Class list, right? I think we need to do abstract here actually. Public, yeah, pure virtual functions, right? So this makes the class. So yeah, I thought there was an abstract keyword. Again, it's like too many languages to keep track of. Many languages, right? You would have abstract keyword, right? Here we're saying void, virtual void, insert, remove, print, right? So a list, a generic container, right? Generic data structure, right? So this means, right? We will need to input the function in the right classes, right? So let's derive it. Our class array list, right? This means we are going to use arrays for this. Private integer array size capacity, right? That's private, right? And we need public facing. Publicly, we need to implement these things, right? We need to implement, right? Array list, okay. Integer capacity, right? That's constructor, of course, right? Void insert, right? Easy. Void remove, that's a little trickier. Void print, okay. And we need to close it, right? We need this. Oh yeah, of course we need to delete it, right? Of course, because we need 3. Okay, this looks good. All right, let's take a look at this. Right, so we say, okay, this is a generic list, so abstract list class. So this is a generic ATF for list of integers, right? Abstract data type. So we created our own structure. So basically we said, okay, we don't care. Basically, we are saying we do not care how you do it, but you need to do it, basically, right? You say, okay, I want insert, remove, and print. How you do it? What kind of structures? Up to you. Again, the good news is, of course, most languages already do this for you, but C++ lets you do this very low level, right? So in this case, we have array, right? A pointer to an array size and capacity, right? So insert size. Let's see, how do we do this? Right. So this is here dynamic. This we allocate maximum memory for the array, right? Right. So this is pretty safe. So this is supposed to be safe, right? Again, crucial to free the memory, right? Okay. Now let's use it. Let's use our list. Let's use our list or concrete list class. So basically, this is like array list, right? Insert, right? Print, right? Remove, right? And it works, right? So this creates, this allocates. Right. All dirty work is handled for us. So abstract list. We'll talk more about these classes, right? This idea to show you quickly. A list. It should work. It looks good to me. Yeah, 5, 10, 15, 20, right? So it's more like a stack because we have insert, remove. So this is more like a stack in this case, right? Insert and remove, right? Its functions more of, or array list functions more like stack, right? This array list functions more like a stack, right? Because we are not getting
we are not defining values, methods to insert or retrieve, at specific place, right? So it's more like stack. But again, array list, right? Very basic structure, right? So again, the basic idea, of course, here is that this is a virtual. So I thought there was an abstract keyword, right? For some reason I don't, right? So virtual void, right? Insert, right? I say, okay, you have to use. So what's interesting here is, of course, this 0 part here. Print. Why is this 0? It's just static feature. It doesn't. It seems like you would be able to. Why do you need this 0 here? I mean, as far as syntax, what happens if you remove it, right? I will be tempted, but I don't think it's going to work, right? I think it's not gonna. Yeah, you need to put it. It's nothing, basically, right? That it does not exist, I guess. Yeah. All right. Maybe more explanation on that. Okay, so that concludes the basic introduction to abstract classes. Very basic, right? We'll do more abstract classes and do more on data types. Class with virtual functions. But let's look at the homeworks. Now, this is probably the first and slightly more complex. Because of course the problem is that you will need to read the CSV file. That's the only, and it's not as easy as like in Python, right? You need to read the CSV file, right? Bless you, or I don't know. Bless you is because you were just saying how bad the homework is. Yeah. Okay. Yeah. So first of all, you need to use a 2D array of integers with a new keyword, right? That's one thing, right? And of course, then you need to find the minimum value for the. You have a minimum value for the first column, arithmetic mean for the second column, right? And the population standard deviation. What the heck is that, right? In the third column, right? And of course, this third one is from the. You can look at the Khan Academy or any statistics book, but of course, it says here, right? And then you need to clear dynamically allocated memory. So basically, yeah. Let's look at this example here, the data. 2D, right? Oh, I'm going to open this notebook. The notepad or notepad, right? Okay, so ABC, right? Column names, basic CSV. So you have to ignore the first row, right? Basically. So for the first column, you need to calculate the minimum. For second, the average, mean, and for third, you calculate the arithmetic deviation, basically, right? That's all. So nothing too complex, right? But still, right? So that's why I'm only giving you one homework, and it's done to do in 2 weeks. So you have 2 weeks for this. Okay. So by the way, you can use any library, but I do want to see the allocation, dynamic allocation, right? That's the one thing. Okay. What else? So again, I'll see you guys in algorithms on Tuesday, right, 10 o'clock. Yeah. So some of you will be on a trip, but yes. So who else is not planning to be here? Because not planning on being here. Yeah. You better be here. Right? Because of course the makeup will be slightly harder. Right? Of course. It's only fair.